Alright, in this video we're going to be solving a numerical example of a voltage divider. So in the last video we saw that by basically just finding out the total current flowing through from the input voltage to the ground over here, we derived the following expression for the output voltage. So essentially the output voltage is equal to R2 divided by R1 plus R2, and that's going to be times the input voltage. And this is essentially the expression we got for that. So we're going to be evaluating that, and we know that, okay, we can use this formula. This is quite handy in here. So we're going to have 2, and that's going to be divided by 2 plus 1, which is 3, times 20. So that's going to be 2 on 3 times 20, which is 40 on 3 volts, or approximately 13.33 volts. Okay, so we can see that even though there's a 2-to-1 ratio between the two resistors, the voltage that is coming out from the middle is actually it's pretty much 2/3 of the input voltage. So the relationship is not really necessarily related to the ratio between these two. It's more related to the sum of the resistors and so on. Now, this wasn't the only thing I wanted to talk about. I mean, we can use this formula in any way we want. That's pretty straightforward. But let's try and think about a more complicated example in which we have a resistance or essentially a load attached to this. So far we have considered the cases in which we only have two resistors and we just have the ground. But let's see what happens when we have R1, R2, and now we attach another resistor or a load, which we're going to call RL, which is also connected to ground over here. So can we actually calculate the potential drop across this resistor? So in this case, we could pretty much implement the same thing again. I mean, we could just have a current coming in over here. And then in order to find that, well, first of all, we need to find the total resistance of this circuit. So in this case, our total is going to be given by these two resistors are in parallel, which means that we're going to have R2 parallel with RL, which means we're going to have 1 over R2 plus 1 over RL, 2 minus 1. Or we can just simply leave it in this form just to say, basically have an easier expression. And basically that's just from that, but we're going to have to add to this. So I should probably just add that over here. The resistor over here, so that's R1. So total resistance, which means that the current is going to be equal to the total voltage, which is in this case just V in. And that's going to be divided by R1 plus R2 parallel with RL. Okay, and that's essentially what our current is going to be. Now we're going to calculate the voltage drop across each of these resistors. So voltage drop across the first one is going to be I times R1, which means we're going to have R1 divided by R1 plus R2 parallel with RL, and that's going to be times V in. Now the voltage drop across the second set of resistors is going to be essentially the same because they're in parallel. And what this means is that we're actually going to use the parallel resistance or the total resistance, which is in this case just that. And since the current should be the same for that case, then essentially we're just going to have I times R2 RL. And what this is going to give us is, well, we have this now. We now sub in for I. So that's going to be R2 parallel with RL divided by R1 plus R2 parallel RL times V in. So it turns out that the potential drop across the load is going to be given by this. So it's going to be quite different to what you would normally get if you essentially just have an open circuit over here and just extract the potential at this single point joining the two resistors. So this is a really important thing, because when you're dealing with real circuits, you're always going to need a load, and that load is going to affect how much voltage or current you can get out of that. And of course, you could use the same thing to calculate the individual currents through each of these resistors, but that's pretty much just applying the basic concepts we already know. In the next video, we're going to extend all of this stuff to multiple voltage dividers, and we're going to see how we can come up with a general kind of formula that basically gives us the voltage across any kind of connection between two resistors in series.